Welcome back. Let's look at this build your understanding problem with the hippocampal region of the brain. So the hypothesis that's being investigated is whether the average size of the hippocampal region of the brain in the students with alcohol problems, or the adolescents with alcohol problems, whether that mean is less than the normal average size. And so our null hypothesis is going to be that no, the mean for this group of adolescents is the same as the normal mean. No difference. Since our alternate hypothesis is a less than, that means the type of test is going to be a left-tailed test. That's because less than stuff is to the left on the number line. Our test statistic is a t, so it's the sample mean minus the assumed population mean divided by standard deviation, which is itself divided by the square root of the sample size. Okay, and the way I computed that, I did the subtraction and got negative 0.92, and then instead of getting a fractional denominator and dividing by it, I went ahead and changed that into a multiplication. You can punch the buttons however you want, but that's what I did, and I got negative 4.55 for my t value. Okay, so for the p value, we're interested in the probability that t is less than negative 4.55. Why that specifically? Well, I'm interested in the probability of having that sample mean be less than or equal to what was 8.10. Okay, so what's the probability that you get a sample mean of 8.10 or even more extremely less than the normal the population mean, the normal hippocampal region size, I guess is what I'm trying to say, and that was 9.02. So this is less than that. Okay, so anyway, so we're looking for stuff to the left on our t table. Now this is, remember with the t we need degrees of freedom, and the sample size was 12, so we're looking for the t with 11 degrees of freedom. Zeros in the middle of the t distribution, just like the z distribution, and so the negatives are to the left, and I want to know what that area is. Okay, so I go to the t table. Now the t table only gives areas to the right, so hopefully you remembered how to deal with that. If I want area to the left, in order to get that from the table, what I'm going to have to do is, well, there's two ways of doing it. I suppose you could try to get area to the right of negative 4.55 and then do 1 minus that area to get the area you want. However, the table doesn't offer us the chance of looking up negative t values. So what you end up having to do is remember that this t distribution is symmetric, and the area to the right of positive 4.55 will be the same as the area to the left of negative 4.55. So let's give a try using the table to find that area. So 11 degrees of freedom, 4.55. So 11 degrees of freedom is here. I'm looking for something as close as possible to 4.55. The closest I see is 4.437. Okay, so the closest I'm seeing on the table is 4.437. And the table's telling me that the area to the right of that, so where did that go? 11 degrees of 4.4. Okay, the table tells me the area to the right of that is 0.0005. So 0.0005. which means that the area to the right of 4.55 is actually less, right? This whole area up to here is 0.0005. So this area is less than 0.005, which means similarly this area is less than 0.0005. Okay, but we'll go ahead and use 0.0005 as our approximation, and then the issue is whether that is less than the level of significance. Okay, so 0.0005, that's certainly less than 0.01, the level of significance. So did you reject the null hypothesis or not? Hopefully you did, because when the p-value is less than the level of significance, that means that the null hypothesis is just too improbable. So we do reject it, but then we state our conclusion in terms of H1, the alternate hypothesis. So we'll say there is sufficient evidence at the alpha equals 0.01 level of significance to conclude or suggest, or some verb like that, to conclude the mean hippocampal volume in adolescence with alcohol disorders, alcohol use disorders, alcohol use disorders is less than the normal 9.02 cubic centimeters. Okay, if you got through that, good job. A couple of sort of miscellaneous notes before we leave this type of test. When can this test method be used? And by this test method, what we really mean is using the t-distribution. In order to use this method with the t-distribution, the population must either be normally distributed or your sample size must be greater than or equal to 30. You'll probably need this information to answer a couple of homework questions. As far as I'm concerned, you don't need to memorize this. I'm unlikely to ask you about that. In fact, let me just commit myself. I'm not going to ask you about this, but you will probably need to know that for the homework. So make a note that that's something you can come back to when you're doing the homework. Okay, the other thing I want to mention before we go on is statistical versus practical significance. So we've used this word statistically significant, and we said that results are statistically significant if the difference between the null hypothesis, remember that's the one you assume to be true, if the difference between the null hypothesis and the observed result, by observed result what we mean the point estimate. So observed result, we're talking about what you get out of the sample, the point estimate. So if the difference between the point estimate and the null hypothesis has a low probability of occurring, low enough to reject the null hypothesis, that's when we say that the test had statistical significance. Practical significance refers to whether the difference again, that's the difference between the point estimate and the assumed mean, the assumed value of the null hypothesis. If that difference has practical value, then we'd say it has practical significance. Otherwise, it might have statistical significance, but not practical significance. For example, mean travel time to work was 27.5 minutes in a certain county. Then the county reprogrammed all the traffic lights in an effort to reduce travel time. A random sample of 2,500 commute times is obtained, and with a mean travel time of 27.2 minutes and a standard deviation of 8.5 minutes. Now, when the county tested the hypotheses, the null hypothesis being that recalibrating the traffic lights didn't change the mean travel time. It left it the same, so no difference between the new mean and the old mean, versus the alternate hypothesis. They're checking out whether their recalibration of the traffic lights reduced the average travel time. So when they tested those hypotheses, they determined that there was sufficient evidence at the alpha equals 0.05 level of significance to conclude that the mean travel time has decreased. Okay, so when they say sufficient evidence at some level of significance, okay, that means that what they found was statistically significant. Okay, so they did a normal hypothesis test, got statistically significant difference between the point estimate and the assumed population mean, so they rejected the assumed population mean. But what about practical significance? So in other words, I'm asking you, is decreasing mean travel time by, so what was the difference? The old mean travel time was 27.5, and after recalibrating all the traffic lights, the mean travel time was 27.2. So there's a difference between those two numbers of only 0.3 minutes. At 0.3 minutes, let me put that another way, that is 18 seconds. So average travel time was reduced by 18 seconds. And so the question is this of practical significance? The hypothesis test, indicates that probably really did happen, but is there any real-world practical significance? I don't know about you, but I wouldn't be particularly impressed with having 18 seconds taken off my commute time. So I would say, no, this really isn't of practical significance. Okay, that's a good stopping point. So we will stop there, and I'll see you in the next video when we will probably go on to hypothesis tests for standard deviation.